So it's my great pleasure to speak here. Thanks to all the organizers. So the main emphasis in this conference is on the geometric structures, and I will be talking about one particular kind of geometric structures which are used in the algebraic geometry. So the emphasis I will be placing on G mod P, and these are special cases of Fano manifolds. Okay, and the interest will be focused on those of Picard number 1. In case of G mod P, this simply means that P is maximal parabolic. A prototype of that would be Hermitian symmetric spaces of the compact type, which are irreducible. So, for example, you can take the hyperquadratic, or you can take GPQ, the Grassmannian notation, the Grassmannian of p-dimensional complex linear spaces in p plus q dimensional Euclidean space. I should say that the case of Pn is a special case of this, but that is taken to be, in a certain sense, exceptional. So the exceptional spaces are more generic than the projective space in some sense. Okay. Now, so there's another word in the title of my talk, which is for analytic continuation. So, of course, this is a notion of fundamental importance already in the theory of functions of one complex variable. So, in the 19th century, but this concept, however, gave rise to actually the theory of functions of several complex variables. And that was the notion of Karpov phenomenon. This has to do with the following, but this is not the simplest case, but if you take n, and these two, and you take, so a holomorphic function f defined here, d by f, so holomorphic function, then f extends to the ball. So in other words, well, what happens outside already determines what happens inside if the function is to be extended analytically. And actually such an extension exists. So this is the famous Hartogs phenomenon, and it has some relation to the notion of causality in physics. So if you're talking about space-time and regions in space-time, the fact that the certain events, any event describable in holomorphic functions over a region determines what happens elsewhere is a notion of causality. Okay. Now, so how do I link the two together? Let me link the two together by a simple example. Let's take a situation of, consider the following sort of obvious theorem. So you take, so f, take a 2-ball into C2 and assume that f sends, so let's say the df, determinant of df is not equal to 0 at one point. Assume f sends pieces of lines, of affine lines. Pieces mean open subsets to into affine lines. Then this implies that actually f is the restriction of a projective linear transformation. It's reminiscent of the fundamental theorem of projective geometry. But well, how does one, there are many different proofs of this elementary statement, but I want to mention one proof which brings into a connection between the notion of analytic continuation and the theory of Fano manifolds. I should say, of course, here, when I say that, well, G mod P are Fano manifolds, what I have in mind actually is the following most important object of study, namely lines. So I will be studying lines on G mod P and lines on Fano manifolds in general.
No, you have to exclude complex conjugation though, I suppose.
A holomorphic map. This F is a holomorphic map.
Oh, it's a holomorphic?
Yeah.
Ah.
Okay. The way to prove it is the following. If you look at, okay, this is my ball, however small it is. So here there are many lines here. Okay. Any line is transformed into a line. And the line actually here is defined by a point in the dual space. So you think about B2 not as B2 in C2, but rather as something inside P2. So you can say this is the Harris-Chandra embedding. But more important thing is here, this is the compactification. Okay, so a line here is defined by following equation. So let's say I use coordinates Z0, Z1, and Z2 here. And look at, so this is the equation whose zero set would define this line, or rather its compactification. Okay, now the question is, well, the assumption is that you have a map associated with this, and I would call this F sharp. Into P2 dual, and this is also inside P2 dual, which is in itself isomorphic to P2. The dual is simply the space of lines in P2, or of minimal rational curves on P2. And the question is to describe this set U. And to describe this set U, well, it's defined for a certain point here, provided that it has non-empty intersection with the two ball. So when would it have non-empty intersection? So line L are defined by and L intersection B2 would be non-empty if and only if the following distance is less than 1. So, okay, if and only if you can do this simple computation to get the following. The distance of the 0 to the line L is less than 1. So that's the same as saying that so this implies so if you use the inhomogeneous coordinates, you might write this as being W1 squared plus W squared, 2 squared being bigger than 1. In other words, if you describe this open set script U inside the dual projective plane, this would be the open set which is the complement of the unit ball. So U is equal to the complement of the closed unit ball. So this is pseudo-concave. Well, this is already the like the Hartog's phenomenon. You will have a region which includes not just this ring, but everything outside. So excluding only a ball here. And if you have a certain holomorphic function that's defined outside, and by Hartog's extension is extended inside. And the same holds true for meromorphic functions. So when you talk about maps, it becomes meromorphic functions, but you still have the extension. So this being the case, it means that this map F sharp extends to something, let's say capital F sharp from P2 dual into P2 dual. It's a meromorphic map, and well, the important thing is that you have global extension, and then you can recover an extension of small f. So how do I define? I want to extend this f outside. I start with something which is defined here with certain properties, and now I want to define it outside. Well, how do you get a point here? Actually, a point is transformed to the intersection of the images of the lines passing through the point. So this is fundamental in duality theory. And so you can look at, so inside you have this, you have fx equal to intersection of some transform of L, so L containing x. And this holds true inside, and then you define it to be like this outside. So then you get a map. By taking the intersection, you get a map. So f is then extended. So f is then extended to something, let's say f tilde from P2 to P2 by taking intersection. And well, and this is just well, very close to proving that this is projective linear. And in fact, the projective linearity follows very simply. Okay, so this is a situation where you can see analytic continuation related to lines. So there are two objects here. One is the study of lines on Fano manifolds, or on, well, first of all, on GMAP, and there is from several complex variable the phenomenon called Hartog's phenomenon, and the two are tied together in the proof of this very simple statement, which is sort of well, an extension theorem. But this is an extension theorem from a small open set, so to speak. But you do it by passing to a big open set when you impose a condition on preservation of lines. Okay, so this is by way of background. The link between study of Fano manifolds and analytic continuation.
You said that this map is meromorphic.
Yeah.
But why is it not holomorphic?
Well, whenever you take intersection and this kind of things, and the degeneracy singularities could occur. So a priori it's meromorphic. You do a little bit of more work to prove that it's holomorphic as a map from P2 to P2. Yes. As a map from P2 to P2. When you define map set theoretically by taking intersection, there's a possibility of jump of dimensions and so on. So in principle, it could have sets of indeterminacies. Then you argue that this is not the case, and it's not difficult. But so as to this, the problem I'm going to explain today, this is what the background of what I'm going to talk about would have some connections with John worked with most earliest work with Tsai, and then a program on the study of Fano manifolds with Huang, and then the most recent result I'm going to talk about would be John work with Holmes. So. Okay, now there are two sources of problem, one from several complex variable. And another is from algebraic geometry, notably on Fano manifolds. And here, this is a focus on the study of what are called minimal rational curves. So what I'm interested in is actually to draw some relationship between two types of problems, and as a matter of fact, try to tie in the methods arising from the study of Fano manifolds the minimal-rational curves with problems of extension with several complex variables. Okay, now, so this very simple argument about analytic continuation was used in an article in 1992. This is with and in this article, we prove the following. Suppose we take omega Cn to be an irreducible bounded symmetric domain. And suppose the rank omega and equal to 2, and let f omega into be an open embedding by holomorphism onto a convex open subset 1 if omega and the convex subset D, if D is bounded, then we prove that f is up to affine transformations and holomorphisms of omega, the Harris-Chandra embedding. So in the context of complex analysis, when you deal with geometric structures, and when the geometric structure is semi-simple, actually the prototype is that of the bounded symmetric domain and their quotients. So some geometric structure theory is used in the proof of this statement. And the next is that if D is unbounded, then F is the Cayley transform. Is a partial Cayley transform. Examples of that is the following. Suppose you take the type 3 domain of genus N. This consists of the set of all matrices Z, so symmetric n by n matrices with complex coefficients such that I minus Z bar transpose Z is positive. So this is the type 3 domain of genus N. And then you have the zero upper half plane, so the set of all tau, again symmetric, but with the condition that imaginary part of tau is positive. So this is a Cayley transform. This is actually a total Cayley transform of this domain, and then of course this is also convex. So the statement is that all convex realizations are given by the Harris-Chandra embedding together with the partial Cayley transforms up to the obvious modification you can make, preserving convexity, namely affine transformations. Okay. Now, so just a few words about the proof. It's not an easy proof. So take this domain, and let's say some convex set here, bounded or unbounded. Let's take the bounded one first. And inside here there's a lot of structure. So there's called the boundary component structure. So for instance, you can consult Joe Wolf. Geometrically, what it means is that you have a lot of products inside. And on this product, it looks something like polydiscs. In fact, it can be a polydisc, or in general, it could be a disk multiplied by a bounded symmetric domain of lower rank. And then on here, you can consider the boundary values. You go to the boundary. You can consider boundary values, And how is convexity used? Well, when you take a limit on the boundary, the fact that you have convex domain implies that this guy would lie inside some linear subspace of a affine linear subspace on the boundary. Then you have to study the structure of the affine linear subspaces. So this is, well, even by today, it's still not an easy task, but this can be done. Now, so once you have that, then you can consider, let's say, the affine linear subspaces of minimal dimensions spanned by the images of the boundary limits of this lower rank boundary symmetric domains, and then you get some associated meromorphic map into some moduli space. And then you are back to in the picture of the study of the line preserving maps defined above. But this is of course more complicated, but the basic idea is still the same. So you have you will be able to consider maps and which preserve certain set of subsets, and then you have maps going to the certain open sets of a dual space. And in this case, since you are dealing with boundary symmetric domains, they are actually lying inside rational homogeneous spaces, actually the compact type, Hermitian symmetric spaces of compact type. Like if you take a type 1 domain that lies in the Grassmannian, and you can then make use of structure of the Grassmannian and so on to study things, and then you can actually know the compactification very well, and the kind of argument as I sketch for the projective space can be carried out. Now, so this is one first result. And then there's a second result. This is due to a tie. Well, actually, so I raise a problem in relation to Hermitian metric rigidity, and this is a problem on proper holomorphic maps. And the conjecture which finally became a theorem proven by Tsai in 1994 was the following. Suppose you have omega going into omega prime, and suppose rank of omega is bigger than or equal to 2, and rank of omega prime is less than or equal to the rank of omega, and you assume that this is irreducible, so omega irreducible, and then you have a map F which is a proper holomorphic map. So F is a proper holomorphic map. Proper holomorphic map means that when you take a sequence going to the boundary, the images would go to the boundary. And in setup, as I explained, you can take boundary values on products. These are just the non-tangential limits. Okay, you're taking non-tangential limits on the boundary. Then the fact that if you have this picture, maybe this is embedded inside something like here. When you take boundary values, they would have to lie on the boundary. And then you have a setup which looks very much like what I said before. And in fact, the picture is easier here because you know the structure of the boundary components much better here. For the convex domain case, is even more difficult to analyze. Here, you know the structure of the boundary. There's some moduli spaces of boundary components which can be embedded into a complex, actually rational homogeneous spaces, and then you can make use of the type of argument for analytic continuation. Okay, so this was proven by Tsai, but in his proof actually make use of Kähler geometry. So in the use of Kähler geometry, one has to make use of the Berman metric. So, well, of course, this was in 1994. Okay. Now, while this gives a proof, I found this conceptually not the most satisfactory, because the problem of studying proper holomorphic maps is a problem which is completely complex analytic in nature. And of course, it's geometric, and I would like to see a proof which is which in some sense gets rid of the use of smooth objects such as K. Now, so in another apparently completely different direction, so since 1997, I have been working with Huang, and this is a program what we want to call geometric structure of projective uniroot manifolds, a model on VMRTs, and this is part of the title. This is the varieties of minimal rational tangents. Let me explain with examples. Okay. Okay. All right. First example is the following. If you take Pn and you take a hypersurface, so this is xd. Let's take n sufficiently large, let's say. Okay. So the first Chern number xd is actually n plus 1 minus d. And when d is sufficiently small, this is positive. And from the theory in algebraic geometry, namely Mori theory, one knows that there are a lot of rational curves. But actually, in the case of hypersurfaces, you can actually, in principle, write down or design an algorithm to solve for the space of lines on them. So the rational curve of minimal degree would be of degree 1, so they are lines. So you have to find the space of all lines lying on them. And for instance, if you take something like Picard hypersurface, Fermat hypersurface, and suppose I start with a certain point for which this is satisfied, so let's take a point there. Belonging to, this is my variety xd. And you look at tangents, so you want to solve, so find all w0 and wn such that x is 0 plus t the w0 to the power d plus xn plus t wn raised to the power d. This is going to be 0 for all complex number. And then you expand, you get a certain number of equations by equating the coefficient to be equal to 0. And the number of equations depends on the degree. When the degree is small enough, then you have solutions. And this also corresponds to the fact that when you compute a Chern number, you would need a certain bound on the degree to make the Chern number positive. There's a case where the Chern number becomes 1, in which case you don't have lines, and you will have to find quadrics inside them. But let's say we're just interested on lines for the time being. So if you have a hypersurface of sufficiently small degree, actually you can prove that this is uniroot by lines. So there are a lot of lines here. And in this case, since you can write down the equation, you also see the space of lines passing through this point. You can write down an equation, and it becomes, when you equate the coefficient, you get sums of powers, the same powers of the coefficients. And then you can see that actually, so let me give it things names. So I take C, the point X, to be equal to a set of alpha such that there exists a line, a projective line on X passing through small x and tangent to alpha. So then in this case, alpha, the Cx is actually complete intersection. In these examples. And actually this is the case when you have low degree hypersurfaces. Okay, so these are what one calls the VMRTs. Now in the case of submanifolds, unirule in this case means filled up, let's say, just filled up by projective lines. At every point there's such a line passing through it. Then actually one doesn't need too much abstract theory. If you want to parameterize all lines passing through it, it's sufficient to take the space of directions, of tangent directions, since in each tangent direction there can only be one line. And there's an isomorphism between the moduli space of marked minimal rational curves passing through a point and the space of directions tangent to such lines at that point. In each direction there's only one. And actually, this is the case for a general point on the hypersurface or on the projective submanifold. Now, in general, one needs, of course, some more elaborate theory, and this theory comes from the Bannon break by Murray, and this is not the conference in algebraic geometry, so I would just say that what is known. But perhaps before going on a little bit of a general theory, let me say that another prototype of examples of special interest to us are the rational homogeneous manifolds, so we take G mod P. And this can be embedded into, so for instance, simplest example is this inside P n plus 1 hyperquadratic. Another is you can take the GPQ, and then you can take let me W, where W is isomorphic to CP plus Q. So this is a Kluger embedding. So you can define the notion of lines here by using from the point of view of Lie groups, but you can also define it after doing the embedding. And in any case, there's the SL2C orbits here of the roots. Then it gives rise to actually minimal rational curves here. And they are actually they're actually lines. So they are lines lying on this Grassmannian. Okay. Now, what are the VMRTs here? Or the VMRTs can be described in terms of G structure. And actually, if you write omega or this is the real notation, and you write the compact dual as GC mod K, then KC orbit of the highest weight vector gives VMRTs. But this requires a proof. For instance, the hyperquadratic, they correspond to null geodesics. Now, okay, so in this example, you can see that there is a certain set which underlies the geometry of the domain or the manifold, and as a matter of fact, it can be one can justify the statement that all the geometry actually comes from these VMRTs. Okay. Now, in the case, for instance, of hypersurfaces, where the VMRTs are varying in general, you may think about the VMRTs in a certain heuristic sense as underlying geometric structure modeled by the variable families of projective submanifolds. In the general theory, one might not know that it is a submanifold that could have singularities a priori, although one doesn't have examples where the VMRTs are generically singular. Conjecturally, they should always be non-singular, but nonetheless, a priori one cannot say that. In any event, you have certain variable spaces of distinguished directions which underlies what one can say a geometric structure. And then for this geometric structure, there are various ways to study it. And then among the first results in this joint program of study with Jim Kwang concerns these VMRTs, and especially a result on analytic continuation, which has a number of algebraic geometric applications. So let me state such a theorem. So the theorem in this form was it says the following. Suppose I have variety x, and let's say they are Fano of paper number 1. The same for that. And suppose I have an open set. And over here you have this fiber bundle, sort of topological fiber bundle at least. A variable fiber space of projects of varieties. And suppose I have a map, small f. It induces a map df. They lie inside the projectives. This is projectivization. This is lying again inside the projectivization Tx prime. And you make the assumption that this distinguished subfamily, for instance, null geodesics, are mapped onto this in a one-to-one manner. So assume that you have this map and df x on C at the point x would give me C. Let me write in this form, assuming things are irreducible. And now, assume that Cx is nonlinear at a general point. And this implies that f extends to a biholomorphism f. What does linear mean? Well, linear means a finite union of linear subspaces, actually of the same dimension. For instance, it could be a finite number of points. So there are finite manifolds for which you have only a finite, at a general point, a finite number of lines passing through them. And it could be a finite union of higher dimensional projective subspaces, but so far there are no examples. But in theory, they may exist. Okay, so suppose you rule out the case where things are linear, then this theorem of Huang and myself says that actually this map extends to a biholomorphism. So it can be taken as a far-reaching generalization of a theorem by Uchia in the theory of G structures. In this theorem, if you look at the case of the hyperquadric or an irreducible bound symmetric domain, and you have a local map preserving this geometric structure, then actually extends to a global biholomorphism. Okay. So, and as I explained, in the case of bound symmetric domains or their compact duals, this G structure actually corresponds to the VMRTs. They are completely recaptured by the spaces of VMRTs. Okay. Now, actually, an earlier version of this was proven in 01. where one imposes some additional condition on the Gauss map on the VMRT. So this is my VMRT. This is my PTXX, and this is my CX. And then at each point you can associate to it as normal, assuming that that is a smooth point. And in O1, we already, so in O1 we already did this under the following assumption, under the assumption that the Gauss map is non-degenerate. So in the sense that the differential of the Gauss map, I say the Gauss map is generically finite. Okay. So some non-degeneracy. Let me say something about the consequences of this theorem. This is I would refer to this as Gartner-Fubini extension. So the Gartner-Fubini extension implies the following. It implies a solution of solution to Lazarsfeld problem. It says the following. So if you take x to be G mod P, and this is Picard number 1, so P is maximal parabolic, and you look at a surjective map. So this is surjective, a finite surjective map. Yeah, so it has to be finite. Then this implies the conjecture, which was settled by Ngaiming and myself, is that actually then G mod P, then so this guy is called F, then either Y is the projective space or F is a holomorphism. So this is the statement of the solution to Lazarsfeld problem. The Lazarsfeld problem was actually first solved in 1999 by Ngaiming and myself, using a lot of the information from theory of differential systems. So especially the work of Ochiai and Yamaguchi. Of course, it uses rational curves, but in this final version, actually, essentially reduces the result to an application of the Gartner-Fubini extension theorem. Okay. Now, as I said, in O1 there was already this special case, and it's this special case which I will explain a little more. So actually, I was trying to explain the continuation, and I want to explain it in the context of several complex variable. And I explained already, for proper holomorphic maps, one can make use of boundary values to get, but for convex embedding, one can make use of boundary values of this holomorphic maps. So when I explained High's theorem, I wanted to give a proof that gets rid of the use of Taylor metrics, and this, so in place of the Gamma metric, we can make use of the geometries of VMRTs, and it's the following. So okay, so as I explained, so to explain this, let's look at a simple example. So you have proper holomorphic map. So let's say this is D1PQ. So this is the dual to the Grassmannian GPQ, and this is the RS. But you assume that the rank, let's say, so the minimum of PQ is actually equal to the minimum of RS, and you assume this to be at least equal to 2. And then you look at boundary values. By looking at the boundary values, one gets the following. Now, what are the boundaries here? The boundaries here are actually domains of the following type. You can So if you take a biosymmetric domain like this, given by matrices, so you will have products like this. So you will have actually this cross D P minus 1, Q minus 1. So if you look at a face on here and look at tangent to the face, a tangent can be interpreted as a matrix, and the rank of the matrix has to drop by 1. And you go to the boundary. Now then, by looking at the boundary values, you get maps. And then you do this an argument for analytic continuation. You can come to the conclusion the following. That's actually the map df transforms at a general point matrices of rank 1 to matrices of rank 1. These boundaries are mapped to boundary. For instance, if you are in the rank 2 situation, along the boundary, the tangents are actually matrices of rank 1, and they are transformed to matrices of rank 1. And this condition can be forced to the interior. Okay, let me correct this. For this argument, actually, I just have to take boundary values, and I can, well, you take for 2 lambda, you can take boundary values, and then essentially use Cauchy integral formula. Already that allows you to say that this statement, that the map transforms rank 1 matrices to rank 1 matrices is a fact not just of the boundary, but actually of the interior. If a property is preserved in the boundary from the Cauchy integral formula, we can conclude that it's preserved in the interior. At least a property such as I mentioned. Okay. Okay. So this condition. So far no analytic continuation is used. This condition is precisely the condition of saying that it preserves. What? It transforms VMRTs into VMRTs. So df of Cx is inside C. So you have this property. Now that's the general situation where things are mapped into a project space. That has to be ruled out. And after ruling that out, you can get the following. Not just this. The image of this is actually equal to a linear section. Okay. Now, we call this VMRT respecting maps, a map which respects VMRTs. And if you have that, so for VMRT respecting maps, plus a Gauss map condition. This is a condition which is a generalization of the genetic finiteness of the Gauss map. But here we are dealing with the non-equidimensional situation. So this is non-equidimensional. For lack of time, I will not specify it. Under these assumptions, then this implies analytic continuation. Okay. So it's along this line that I was able to give a new proof. Well, actually, I only wrote down the case of the Grassmannian, but this proof can be made to work in general. In which the conjecture regarding, or the theorem of Tsai regarding proper holomorphic maps can be solved without making use of Kähler metrics. So this is more in the favor of geometric structures that one gets a solution to that. Now, once you can do that, of course, you can ask to what extent this can be cast in a general context. Well, there is, first of all, the local question. I should mention that the fact that this implies that it comes from a standard embedding, this was also this was proven by Neretin by a study of the matrices. Okay. But here we are doing this geometrically, and which allows allows one actually to move outside the framework of bounded symmetrical domains and even rational homogeneous manifolds, and one can do this in general with Fano manifolds. Okay. Now, so finally, let me state a result that proof. This is regarding the last step, or this. So assuming that actually I have, so you take, let's say, so a standard embedding. So for example, something like G P Q embedded in G P plus A. Take a model like this. So there's a pair. So the conditions will have to be placed. So this is a situation where you have G0 mod P0 being embedded in the G mod P, and I will say what conditions can be imposed on the parabolics, and for this to be valid. So the statement says that for certain pairs of this, suppose U is an connected open subset, and df and f u inside G mod P equal to x is a holomorphic embedding respecting VMRTs, then f extends to a standard embedding that is an embedding defined group theoretically f from. So the Grassmannian was one case which was used in an earlier work of mine, but this is much more general. We prove under the following assumptions. So of course, we assume that this is maximal parabolic. So suppose this is proven under the assumption that G mod P is associated to a node which is a long root, and this G0 mod P0 actually corresponds to a marked Dinkin subdiagram. So this means when you say this, so for instance, you take E6, you take any of these nodes, well, they have all the same length, so you take a certain node here, so then this defines a certain G mod P, and this is then the marked Dinkin diagram is marked at the node, and if you take the Dinkin subdiagram, so let's say I can take something like this. This is G0 mod P0, and you assume that G0 mod P0 is nonlinear. Then this theorem of analytic continuation holds true to give not just an extended map, but that the extended map is the standard embedding. The extension makes use of the Gauss condition. The fact that this standard embedding has to do with the notion of parallel transport, and this has to do with this geometry of VMRTs. I won't have time to explain further on that, so let me stop here.
Any questions or comments?